Today we're going to talk about inner products and norms. First, let's review some ideas from the last lecture on limits of sequences of complex numbers and matrices. First, let's consider a sequence of complex numbers, which we'll denote by z sub k. Writing this expression here, the limit as k increases without bound of z sub k equals a complex number z sub infinity means the following. Given a real number epsilon that's positive, we can find a real number delta that's also positive, such that in absolute value, z sub k minus z sub epsilon is less than epsilon whenever k is greater than delta. We'll also say that our sequence converges to a limit z sub infinity. Similarly, the expression the limit as k increases without bound of z sub k equals infinity means the following. Given a positive real number epsilon, we can find another positive real number delta, such that in absolute value, z sub k is greater than epsilon whenever k is greater than delta. We'll also say that our sequence increases without bound. Here's a picture to kind of explain what's going on. You'll see that either the blue dots, the red dots, or the green dots corresponds to our sequence of complex numbers z sub k. Remember that every complex number is in the form a plus bi, where a and b are real numbers. So we can identify a complex number with a point a comma b in the real plane. Here, by saying that our limit of the z sub k equals z sub infinity, we can think of either the green dots or the blue dots. The idea is that the sequence here is just a collection of points that's moving along, and it'll get closer and closer to a certain point. In the case of either the green or the blue, you can see that z sub infinity will be the center of these either green or blue circles. Here's a specific example. Let's fix a complex number lambda, and let's consider the sequence z sub k equals lambda to the k. Here we're just looking at the sequence that corresponds to lambda, lambda squared, lambda cubed, and so forth. Well, depending upon the choices of lambda, we can actually compute what the limit z sub infinity is. For example, if the absolute value of lambda is less than 1, then our limit z sub infinity is 0. If our absolute value of lambda is greater than 1, then our limit z sub infinity is itself infinity. We're going to generalize these ideas to limits for matrices by explaining the relationship to p-norms. Say that we have a sequence of matrices we'll call A sub k. Then the following three are equivalent for an m by n matrix L. First, for every extended real number p between 1 and infinity, we can find a delta such that, given a positive epsilon, our p-norm of A sub k minus L is less than epsilon whenever k is greater than delta. Similarly, this is the same thing as saying that for some extended real number p0 between 1 and infinity, we can find a positive delta such that, given any positive epsilon, the p0 norm of ak minus L is less than epsilon whenever k is greater than delta. And finally, this is the same as saying that we have mn limits of sequences of complex numbers by looking at the ij entry of our matrices. For example, we could take a look at the ij entries of the matrices A sub k, and now consider what happens when we have the limit as k increases without bound. This here should be equal to Lij, that is the ij entry of our matrix L. These three statements are all equivalent, and if any of these holds true, then we will say that the limit of k increases without bound of our matrix A sub k equals L, and we'll just simply say that our sequence converges to a limit L. The whole point of this proposition is to say that there are many different ways in which one can define a limit, because there are many different ways in which we can say that one matrix is close to another matrix. The point is that all of these methods, all of these definitions, will be one and the same. We'll state the following without proof. Again, say that we have a sequence of matrices A sub k, which perhaps converges to a limit L. First, we can multiply every matrix by a scalar c, and then the limit will tend to c times L. Second, we can multiply on the left by a matrix P, and our limit will be P times L. Next, we can multiply on the right by a matrix Q, and our limit will be L times Q. And finally, If each of our a sub k is actually a power of a matrix a to the k, and we can multiply on the left by some invertible matrix Q inverse, and on the right by our matrix Q, then the limit here of Q inverse A raised to the K times Q is just Q inverse times L times Q. The point is that we can have various operations and the limits behave accordingly. But today, we'd like to introduce the concept of a standard inner product. Let's denote F as the collection of complex numbers. Recall that given a complex number z of the form a plus bi, we can define its absolute value as the square root of a squared plus b squared. We also define the concept of a p-norm. Given an n-dimensional vector x with entries a1, a2 through a sub n, we can define the p-norm in one of three cases as follows. Either we'll have the sum of the absolute value of the entries, the sum of the absolute values of a sub k when p is equal to 1, or we can take the sum of the pth powers of the absolute values and then take the pth root of that. Namely, we'll have a sum over j of the absolute value of a sub j raised to the p, and then we'll take the pth root of that sum. That'll be if p is between 1 and infinity. Finally, if p is equal to infinity, we'd like to have the maximum of the absolute value of the various entries. So that is, we take the absolute value of the entries, absolute value of a1, absolute value of a2, and so forth, and then we take the maximum of those various numbers. When p is equal to 1, we'll call this the Manhattan length. When p is equal to 2, we'll call this the Euclidean length. And when p is equal to infinity, we'll call this the Chebyshev length. Just to remind you, let's consider again when V is the collection of n-dimensional vectors. So V here is c to the n. And we'll just focus on the case when p is equal to 2. That is, we'll look at our Euclidean norm. The length of a vector x will be the following scalar. That is, we'll simply take the square root of the sums of the squares. This is the same thing as the 2 norm. Using this idea here of the 2 norm, let's define this rather funny map. Here we have angled braces, and this says given two n-dimensional vectors, x and y, we'll return the following complex number. This will be a sum, a1 times b1 conjugate, a2 times b2 conjugate, all the way through a sub n times b sub n conjugate. Again, we're starting with two vectors, x and y, and we're returning a scalar, a complex number. This is our angle bracket x comma y. This map here is known as the standard inner product. The standard inner product has the following properties. That is, let's say that x, y, and z are n-dimensional vectors, and c is some scalar. First, we have linearity. That is, if we take the inner product of cx plus z and y, this is the sum of the scalar times the inner product of x and y, plus the inner product of z and y. We also have symmetry. That is, remember that our inner product of x and y is a complex number, so we can compute its complex conjugate. Well, the complex conjugate of the inner product of x and y is just the reverse. It's the inner product of y and x. Next, we have positivity. That is, if we take the inner product of x with itself, not only is this a real number, but it's a non-negative real number. That is, it's always greater than or equal to 0. And indeed, we have non-degeneracy. So the inner product of x and itself is 0 if and only if x itself is the 0 vector. And finally, we have Lagrange's identity. This is a statement about when we have various complex numbers and how they're related to the product of the two norms. So for example, we can consider the sum over k of a sub k times b sub k conjugate. If you stare at this, this is nothing more than the inner product of x and y. We then have a sum of I less than j of the absolute value of ai bj minus a sub j bi squared. This here now is just a sum of squares. And finally, at the end, we have the product of sums of squares. So really, one way to read Lagrange's identity is to say that we have the sum of squares can be expressed as the product of sums of squares. We're not really going to use Lagrange's theorem identity very much here in this class. We're simply going to use the special case when we ignore the middle sum over I less than j and realize that on the left, we have the absolute value of the standard inner product of x and y. And on the right, we have the products of the two norms, that is the two norm of x times the two norm of y. This inequality we'll come back and talk about many times today. We'll just skim over the proof here so you get a basic idea because we're going to use this concept of the proof over and over today. Listing out our three vectors x, y, and z in this way, and now we can consider cx plus z also as an n-dimensional vector. Now looking at the standard inner product of cx plus z and y, we now say that we have a sum of c times a sub k plus c sub k times b sub k conjugate. And now we simply use distributivity and associativity to realize that this is c times the inner product of x and y plus the inner product of z and y. Let's prove the second statement. Recall first that if z, our complex number, is a plus bi, then its complex conjugate, z bar, is a minus bi. Now let's take the complex conjugate of z bar. Well, the complex conjugate of a minus bi is a plus bi. So the point is that if you take the complex conjugate of the complex conjugate, then you just return to the original complex number. Putting all of this together, we can consider now the complex conjugate of the inner product of x and y. Here we have a complex conjugate of the sum of a sub k, b sub k bar, which is the same thing as the sum of the complex conjugate a bar times b. But now staring at this, we realize that this is the same as the inner product of y and x. So let's prove the third and fourth statements. Let's observe that if we compute the inner product of x with itself, this is just the square of the 2 norm. Indeed, this is just a sum over absolute value of a1 squared plus the absolute value of a2 squared, and so forth. We've already seen that the 2 norm is a non-negative number, and the 2 norm is equal to 0 if and only if x is the 0 vector. We found this before when we looked at properties of p-norms more generally. Let's prove now the final statement. Observe that we have the following identities. First, we can consider the sum over the product ak times bk bar, but remember that when we take the square of the absolute value, this is simply the product of a complex number and its complex conjugate. So we can expand it out as you see here on your screen. Similarly, we can take a look at the sum over I less than j of the absolute value squared, ai bj minus aj bi. Again, the square of the absolute value is the product of a complex number times its conjugate. So indeed, we see the sum that you have here on your screen. Adding these two together, we do indeed see that we just have the product over the 2 norms. And ignoring the sum where we have I less than j, we now simply see that the absolute value squared of the inner product of x and y is less than or equal to the product of the square of the 2 norm of x times the square of the 2 norm of y. We're going to use some of these concepts now to define more generally what we're calling inner products. We'd like to extend the concept of the standard inner product on our n-dimensional vectors to something for, say, m by n matrices. Here we'll write a general definition. Let's say that V is any vector space over the complex numbers. We'll say that a map, which we'll write just like before in terms of angle brackets, as an inner product if it takes two vectors, x and y, and returns a complex number, which we'll denote by angle bracket x comma y. We want this map to satisfy 4 properties. First, it should be linear. That is, the inner product of cx plus z and y should be the complex number times the inner product of x and y plus the inner product of z and y. Second, we want there to be the property of symmetry. That is, if we were to take the complex conjugate of the inner product of x and y, this should be the inner product of y and x. Third, we should have positivity. That means the inner product of x with itself should be a non-negative real number. And finally, we should have non-degeneracy. That means the inner product of x with itself should be 0 as a complex number, if and only if x is 0 as a vector. Here we'll give an example. We've already seen that when V is the collection of n-dimensional vectors, then we have the standard product. This is our angle bracket that takes two vectors x and y and returns a complex number. Now let's write down many more examples. Choose n positive real numbers, r1, r2 through r sub n, and let's consider this new map, which we'll call angle bracket prime, that takes two vectors x and y and returns now the following sum: r sub 1 times a sub 1 times b sub 1 bar plus r sub 2 times a sub 2 times b sub 2 bar, and so forth. The claim is that this is also an inner product. Actually, what this shows is that there are infinitely many inner products on our n-dimensional space. So we have to be a little bit careful here. There is no such thing as saying that there is an inner product on V, but in this case, there are infinitely many. So we'd have to know which one are we actually choosing once we do the problem. We'll try to quickly explain why this proposition is true. In order to show this, we really have to verify that there are four properties which are valid. For linearity, it's a matter of realizing that the proof is almost exactly the same as before when we proved this for the standard inner product. For symmetry, again, the proof is almost the same as what we worked out for the standard inner product. For positivity, first let's recall that r sub k should be a positive real number, and the absolute value of each coordinate a sub k is a positive real number, at least not negative. So now we have the sum over non-negative real numbers, r sub k times the absolute value of a sub k squared. But now for non-degeneracy, let's first say that x is the zero vector. This means that each component a sub k is 0, so the absolute value of this complex number a sub k is also 0, so that the inner product of x with itself is a sum r sub k times a sub k squared, which will be 0. Conversely, let's say that the inner product of x with itself is 0 as a complex number. Since the product rk times the absolute value of a sub k squared is non-negative, and the scalar r sub k is positive, we see that we must have the absolute value of each coordinate a sub k to be 0 if the inner product of x with itself is 0 as a scalar. But then this means that each component a sub k has to be 0 as a complex number, so that x itself is indeed the 0 vector. Let's generalize this even further. Let's say now that V is the collection of m by n matrices. More generally, let's pick m times n positive numbers r sub ij, and let's consider our new map, angle bracket, which takes two matrices, A and B, and writes down the number that you see here on your screen. Here we'll sum over row I and column j of the product r sub ij times A sub ij times B sub ij conjugate. The claim is that this is always an inner product. First, let's make a definition before we sketch over the proof of this. Recall that if B is an m by n matrix, then we can consider the transpose as an n by m matrix. Actually, we'll define the adjoint B star as that n by m matrix found by computing the transpose of the complex conjugate of B. That is, we'll simply take the complex conjugate of the entries of B, and then we'll take the transpose of this matrix. When each Rij is equal to 1, then the Frobenius inner product is simply the trace of B adjoint times A. In other words, it's just the sum over the entries I and j of Aij times Bij conjugate. Here, again, all of the Rij's are just equal to 1. As a remark, the Frobenius inner product reduces to the standard inner product when either m or n is equal to 1. As a corollary to all of this, you'll note that there are infinitely many inner products on our collection of M by N matrices. Indeed, one example of an inner product is the standard inner product. Another example is the Frobenius inner product, but even then, we still have infinitely many examples. So just like before, when we're dealing with M by N matrices, we first have to know which inner product we're referring to before we can work out the problem. If we'd like to prove that this more general map is an inner product, again, we have to show that four properties hold true. First, for linearity, the proof works almost exactly the same. Next, for symmetry, again, the proof works almost exactly the same. And for positivity, just like with the n-dimensional vectors, the proof works almost exactly the same. We're going to end today by discussing the concept of norms. We'd like to figure out how do the p-norms relate to this concept of inner products we've been discussing. For this section, let's let V be any vector space over the complex numbers and say that we've already chosen an inner product, our angle bracket. Since the inner product of a vector x with itself is non-negative, we'll define the norm of our vector x as the square root of the inner product of x with itself. Here's our main theorem. Say that we do have a norm coming from an inner product. Then our norm satisfies the following five properties. First, the norm is positive. That is, the norm of vector x is greater than or equal to 0. Non-degeneracy asserts that the norm is equal to 0 as a scalar if and only if x is 0 as a vector. Third, we have multiplicativity. This says for any scalar c, the norm of a scalar c times a vector x is equal to the absolute value of the complex number c times the norm of the vector x. Fourth, we have the Koshi, Bunyakowski, Schwartz inequality. You may remember that we've discussed this a few times before. This says that the absolute value of the inner product of x and y is less than or equal to the norm of x times the norm of y. And finally, we have the triangle inequality. This says that the norm of the sum of two vectors is less than or equal to the sum of their norms. Any map that we write here in terms of double absolute value signs with the above properties is called a norm. Here's our main observation. If V has an inner product, then it has a norm. This is our proposition, our theorem, 6.2. However, not all norms come from inner products. Indeed, let's consider any p-norm that we've defined so far. The p-norm is an example of a norm, but it only comes from an inner product when p is equal to 2. A vector space V that has a norm is called a Banach space. And a vector space V with the inner product is called an inner product space. In this class, we're not going to focus on Banach spaces at all, but we will focus on inner product spaces quite a bit. We'll make here a couple of remarks. Every inner product space is a Banach space because we can always define the norm as the square root of an inner product of x with itself. We should point out that there are lots and lots of examples of Banach spaces. Indeed, for any extended real number p between 1 and infinity, then we can use our p-norm to define a Banach space. Again, for this class, we won't focus on Banach spaces very much, but we will focus on inner product spaces quite a bit. We'll sketch over the proofs of these 5 statements. First, let's show the first and second statements. Recall from the definition of the inner product that the absolute value, the norm squared of a vector x, is equal to the inner product of x with itself. However, the inner product of x with itself is always greater than or equal to 0 because of the positivity property of the inner product. So this means, by using the non-degeneracy of the inner product, that the norm of vector x is equal to 0 if and only if x is equal to the 0 vector. For the third statement, we want to say something about how the norm of a scalar c times x is equal to the absolute value of c times the norm of x. Here we're going to be a little bit careful about the property that we define in terms of the inner product. we'd like to consider the square of the norm c times the vector x. By definition, this is the inner product of c times x with c times x. Now, since c occurs in the first component of our inner product, we can pull the scalar c out to find our scalar c times the inner product of x with c times x. Now, let's remember that our inner product is symmetric, so we'll reverse the order of the two, and then we'll consider now the complex conjugate of this. So this is equal to our scalar c times the complex conjugate of the inner product c times x with x. Again, since our inner product is linear, we can pull our new scalar c out, and now we have c times c conjugate times the inner product of x with itself. C times c conjugate is just the absolute value of c squared, and the inner product of x with itself is the norm of x squared. Upon taking square roots, we do find that the norm of c times x is equal to the absolute value of c times the norm of x. We're going to prove the last two statements, but to do so, we want to focus on the following identity for any complex number c. Eventually, we're going to choose c in a clever way, a couple of different ways, so we can prove what we'd like to have. Let's first take a look at the norm of x minus c times y. Well, the norm we already know is non-negative, but we can also express the square of the norm in terms of the inner product of x minus cy with x minus cy. Expanding this out in a couple of different ways, we now see that we have this inequality that says 0 is less than the square of the norm of x minus twice the following product of complex numbers, c conjugate times inner product of x and y, plus the square of the absolute value of c times the square of the norm of y. You may want to keep this in mind because we will actually use this on homework assignments later. If we'd like to prove the Koshi Bunyakowski Schwartz inequality, we need to consider a couple of cases. First, let's say that y is the zero vector. Then it's not too hard to show that the inner product of x with y is 0. Therefore, the absolute value of the inner product with x with y should be 0. But if y is the 0 vector, then we see that the norm of y is 0. So we find that this is equal to the norm of x times the norm of y, because again, everything is equal to 0. Let's consider the next case where y is not the 0 vector. Again, we'd like to prove the CBS inequality. Now it's a matter of choosing our c from the previous slide in a clever way. We'll choose it to be the ratio of the inner product of x with y divided by the inner product of y with y. Putting this together, we see that 0 is less than or equal to the norm of x squared minus the square of the absolute value of the inner product of x with y divided by the square of the norm of y. Bringing everything to one side, we then see that the square of the absolute value of the inner product of x with y is less than or equal to the square of the norm of x times the square of the norm of y. Finally, for the triangle inequality, we'll choose a different c. We'll choose c is equal to minus 1. And upon staring at this, we realize that the square of the absolute value, the square of the norm of x plus y, is less than or equal to the square of the norm of x plus the norm of y. Upon taking square roots, we then find the desired inequality. Thanks very much for watching.